we've got a bit of a cult hero. So I'm delighted to introduce you to David Phillips. He was part of the band of brothers that back in 2012, they created the Presto engine at Facebook. So David spent about 13 years working in the big world of big data. And yeah, he's here today to talk to you about the latest and greatest with Presto. So over to you, David.
Thank you. Hey, so a brief introduction to Presto. Presto is a distributed query engine. We designed it so that we could process massive amounts of data efficiently on hundreds or thousands of machines. We built it to use standard SQL so that people coming in from other database tools would immediately know how to use it, and that things like BI tools like Tableau would also be able to work out of the box. We originally developed Presto at Facebook. Before that, we were using Hive, and our data scientists would say that on a good day they could run 7 Hive queries. And so you can't do a lot of analysis when it's taking hours to run your queries. So we wanted to build Presto so that people could do faster analysis. And Presto is now used in production at a number of other companies. We've gotten a lot of great open source contributions to the project. Netflix and Uber have contributed Parquet support. Netflix uses S3 heavily, and they did a lot to make that work well in production. Uber added geospatial support. Bloomberg contributed an Accumulo connector. Treasure Data contributed a MongoDB connector and a bunch of other contributions. And there's a number of companies that have commercial offerings for Presto. Amazon Web Services has EMR, which lets you spin up a cluster. They have the Athena service, which is hosted Presto. Qubel and Treasure Data both have their own hosted Presto services. And Starburst Data has a commercial distribution of Presto, and they provide commercial support, and Presto is their sole business. So they're betting a lot on Presto. They also have a team of around 20 full-time engineers working on it. So we're talking about what makes Presto interesting. We started Presto from the beginning to be a multi-tenant system. We needed to be able to run hundreds of concurrent queries on a single cluster. And we needed to do that without the overhead of spinning up containers or JVMs for every single query. And that also gives us a number of latency advantages and performance advantages. The system has to be adaptive because when you're running hundreds of queries at a time, you can't tune the system for the different workloads or tune the queries for the system. It just has to be able to deal with whatever you throw at it. Presto has a federated design where all of the data that's read or written by Presto comes from pluggable connectors. So you can read data from Hive, you can read data from MySQL, you can read data from Cassandra, and you can do joins between them or read and write between these different connectors. So it provides you a lot of flexibility to query your data where it lives. And everything in Presto is pluggable. You can add your own functions or types or security or resource management or logging. And we needed to do that because at Facebook, we have a lot of internal systems that we needed to integrate Presto with. But being an open source project, that's hard to do, so making it pluggable was a good way to do that. At Facebook, we don't have an internal fork of Presto. We run the exact same open source version and binaries that we distribute to everybody else, and then we have our own internal plugins on top of that. Presto's design supports a number of different use cases that we're going to talk about later in the presentation. And finally, Presto was built from the beginning to be high performance. We've put a huge amount of engineering effort into making Presto be efficient and performant at Facebook's workload. And we focus on real-world use cases that we have and not benchmarks. All right, so now we're going to talk about 4 different use cases that we have for Presto at Facebook. These are not the only use cases, but these use cases are all pretty diverse, and they give you a flavor of what different ways Presto can be used and the different ways that the system can adapt. So the first use case is interactive analytics, which is what Presto was originally designed to do. Facebook has a huge data warehouse that's used by the entire company. We have a lot like engineers and data scientists and managers and people building products, and basically everybody has to be able to quickly and efficiently analyze all the data in our warehouse. They do, in addition to simply typing SQL queries by hand, which a lot of people do, they also use various visualization and dashboarding tools or BI tools like Tableau. All these clusters run 50 to 100 concurrent queries, and these queries have very different shapes. Some of these queries range from like simple aggregations and joins to multi-thousand line generated queries, and the system has to be able to handle basically whatever users throw at it. All of our users are using this system. All the queries that go into the interactive system are users waiting for a result, so it's important that the queries come back quickly. They typically run in seconds or minutes, and if queries come back quickly, users can do more work or they can move on to something else with their analysis. And if it's slow, then it prevents them from doing their job. Batch ETL is the second use case. This is something that Presto has grown into and is expanding very quickly. ETL is processing all the data in our warehouse. It's generating tables that are used for interactive analysis or feeding various downstream products and systems. We use a workflow management system that's similar to Airflow or Azkaban. Airflow was actually built by Airbnb people that were previously from Facebook, and they built it based on what Facebook had internally. The queries in batch ETL are much more expensive in terms of data volume and CPU than interactive. So the clusters there are much bigger, and we have way more clusters for batch ETL. And within that system, it's much more important that the throughput of the entire system is good versus latency for an individual query. There's definitely SLA for some of the queries in the batch system, but overall, it's fine. It's usually fine if queries come in and they queue for several hours as long as they run and complete and are efficient. So another use case that we have for Presto is A/B testing. A/B testing is used when you want to make a change to a product. For example, you want to change the color of a button, and then you want to know how is this change going to affect metrics like click-through rate or revenue. So what people do is they make the change, they roll it out to a subset of the users, and then they look at various metrics about how does the test compare to the control users that don't have this change. When someone's doing a test like this, they need the results to be available in hours so that they can make sure that it's working well and that the data is being collected properly. Because we're doing statistical testing, the data has to be complete and accurate. When you're looking at things like, does this have a 0.5% in click-through rate? You need to know that that change is actually accurate, not because you're missing several percent of the data. Users access these A/B test results through a interactive tool that lets them do slice and dice and filtering across time ranges and various other dimensions. Because of that, we can't just pre-compute all the results. We need to do everything on the fly. And doing that involves joins between massive tables. Typically, there's billions of rows on each side of the join. And these queries need to come back on the order of seconds because it's an interactive tool that people are using. And what makes this problem tractable is that the tool only generates a restricted set of query shapes that we can optimize the system for up front. And finally, the last use case is app analytics, which are external facing reporting tools. Facebook has these Facebook analytics products that anybody can sign up and get analytics for their application that they're building on Facebook. This is also driven by a web interface. The data volumes that we're querying are typically quite large, but for an individual query, it's very selective because users can only see their own data. Because it's an external facing tool, we have strict requirements on latency and availability. And we meet the availability requirements by having multiple active hot clusters, so if one of them goes down, the other clusters can take the load. And these clusters have to run hundreds of concurrent queries because you can have a huge number of external users using the system at the same time. All right, so now we're going to talk about the design of Presto and the various features and optimizations that allow it to handle these use cases. So a brief introduction to the Presto architecture. As mentioned before, Presto is a federated system where all of the data comes from external systems. So a query goes into the coordinator. The planner talks to a metadata API in the connector to figure out what are all the tables and columns and types involved in the query. And then the query executes. It goes into the scheduler, and the scheduler talks to a data location API, which tells it where are all the different parts of the table that I can read. Because Presto is distributed, tables are broken up into a number of different parts. And then the scheduler hands these table locations over to workers, which actually read the data from the connector using the data source API, and then the data flows on through the system to be processed, and then finally either written out to another table or returned to the user. So one of the first optimizations that we had to do, and one of the most important, is predicate pushdown. When you're writing a query, you're typically going to have filters. You're going to be filtering data to a specific time range. So you need to be able to push that into the connector so that you don't have to read the entire table every time. An example of this is for the Hive connector, where you're querying over a range of dates, and then those get turned into partition predicates. And then typically connectors will further push that filter down into the data source. So for Hive, we're pushing the partition predicates into the metastore, and we're fetching the list of partitions. And then the engine also provides a predicate that connectors can use to further filter down when you're doing a complex thing like a regular expression or any other anything else that's more complex than like a simple range or list of values. And then connectors can also report back to the engine what they can guarantee about the data that's being queried. So for example, of Hive, when you're querying over partitions, the connector can tell the engine, here's the set of partitions that I'm going to be reading, and this is the range of the data. And then the optimizer can use that to know that if it's joining two tables and they have these ranges, maybe they don't overlap, maybe they overlap in a certain way, it can use that to build better plans. And then the engine can also skip adding redundant filters on data where it knows that the connector is always, where it knows that it doesn't need to add a filter if the data is already constrained. So data layouts is letting the engine take advantage of data that's already been physically organized. So an example of this is a table might be sorted, it might be hash partitioned, it might be grouped in a different way, and the connector tells the engine about it, and then the engine takes advantage of that when creating a query plan. An interesting feature is that tables can actually have multiple layouts. Like you might have a table that's sorted in two different ways, you might have a table that's hash partitioned on different keys, you might have some layouts that only have a subset of the columns or a different range of the data. Like you might have one layout that has this month's data, and then you might have another that's stored in one way, and then you might have a different layout that has all the historical data that might be optimized for storage efficiency instead of query efficiency. And then based on the query that's being run, the engine picks the best plan picks the best layout at runtime. So here's an example of a query plan on the left for a query that's doing a join followed by an aggregation. And in the normal case where you don't have any physical data layouts to take advantage of, we have to insert several shuffles into the plan. So going into the join, you have to redistribute both sides of the join on the join keys, and then you're doing an aggregation, and then you have to further redistribute the data on the aggregation keys. And then on the right, we have a plan that's optimized based on the layout. So if the data's already been hash partitioned on the join keys and on the aggregations, the engine can eliminate those shuffles, and we can do everything in one stage. And furthermore, connectors can guarantee that, like say when you're doing a join, both parts of the join are parts of the data on both sides of the join. It can guarantee that the corresponding keys will be on the same physical machines. And then it can do a co-located join where no data has to transfer over the network. We actually take heavy advantage of this in the A/B testing use case. When we're joining billions of rows and you need the queries to come back in a few seconds, you can't be transferring billions of rows over the network, even if your network is really fast. Queries often have to perform hashes of data. When you're doing a join, you have to hash on the join key. If you're doing aggregation, you have to hash on the aggregation key into the hash table for the aggregation. And then you also have to do those for when you're doing shuffles. So if you're doing a join, you've got to hash the data to go to the right machine, and then it's got to hash again on the machine when it's doing a join. So we have an optimization where we actually pre-compute the hash early in the plan, basically add it in as a hidden column, and then carry it on through the plan. And that can save a substantial amount of CPU when people are joining on like large strings or other complex data types. All right, so intra-node parallelism is adding explicit parallelism into a query plan where it doesn't exist naturally. So an example of natural parallelism is table scans. Tables are broken up. You send those out to lots of machines, and it's easy to run the table scans in parallel because you simply read from the different chunks. But then you've got things like building a hash table where that's not naturally parallel, and you have to actually do explicit work to divide up the data appropriately so that you can build a hash table in parallel. And believe it or not, we actually didn't have this feature in Presto for several years, and it worked fine because most of our use cases were, the early use cases were interactive analytics, and we'd have 50 queries running at a time. So even if you only had 1 or 2 threads per query per machine, that was fine because you have 50 queries that are going to be using up the entire machine. But then once we started doing stuff like A/B testing, where we need a single query to be able to maximize all the cores and all the machines at the same time, we had to do work to add in more parallelism. And then this became useful for both interactive analytics and ETL, where you have skew. Skew is you might have a whole lot of values for a single aggregation key, and then those all get sent to one machine. And then you want that machine to be able to plow through the data as quickly as possible. It's especially important for the interactive use case where people write queries and they don't really think about optimizing it, especially if they're doing exploratory analysis. You don't want people to spend an hour writing a query that you're going to run in a few seconds. And so having extra parallelism on each machine can help with those cases. Now, here's an example of a execution plan where we take advantage of multiple threads on a single machine. So we have, this is a stage for a join. We can see in pipeline 2, we have table scans that are scanning the data, and that's naturally parallel. You can run as many table scans you want. You just add more splits to each machine. And then pipeline 1 is building the hash table, and we have to explicitly insert a shuffle between there so that we can break up the data and into different parts and then build parts of the hash table in parallel, which then feeds into the join. So queries are broken up into multiple stages for things like joins, where you have a join, you need to distribute the data, you need to distribute both sides of the join on the join keys, and you'll have one stage that's executing the build side of the join that's building the hash table, and then you'll have the other side of it that's actually using the hash table from the join. And then you have, underneath those, you have the table scans or subqueries that are feeding data into the join. And so you have a couple choices on how to execute that. So the first way is you schedule everything all at once. You start building the join, you start reading the data that's going to go into the join. And then the data that's going to go into the join, it'll block until the hash table is ready to be used. And for things like interactive analytics or A/B testing, you want those to, you want to start everything immediately because that reduces latency. When a query is only going to take a few seconds, it's fine if you're using some extra resources because you're not going to be using them very long. For the batch ETL use case, we want to minimize resource usages, so we use a phase scheduling approach. Building a hash table might take minutes or hours because you could have a very complex subquery that's actually the one building the hash table, and then you don't want to be tying up a bunch of memory and other resources while that's happening. So we use a phased approach where we keep track of the dependencies and we only start things as they are necessary, and that can be a substantial reduction in memory usage, which is actually one of the biggest bottlenecks in our clusters for batch ETL. So unlike other systems like MapReduce, which enumerate all of their work up front, they figure out what are all the files and where are all the splits and what's all the work I have to do before they start executing. Presto enumerates things as it goes. So it'll go to Hive, it'll get the metadata for a single partition, it'll go to the file system, it will list the files in the directory, and then it'll immediately start executing for that first split. And that reduces latency. And for interactive queries, this can be a huge deal because you might have a huge number of partitions, and enumerating all those could take minutes or longer. And often, users are not reading all of the data. Like they might be using a tool where they just want the first few thousand rows, so it doesn't make sense to spend a bunch of time enumerating work that you're never going to execute. Another thing this helps with is reducing memory usage on the coordinator. We have tables that have millions of partitions, and those partitions also have millions of files. And if we try to enumerate everything up front, we would quickly run out of memory in the coordinator. So doing it in a pipelined approach where we only figure out what we need as we go allows us to handle those gigantic tables. And we also don't eagerly assign work to workers. We do it basically also as we go. Workers have a queue, and then we can assign work to workers with the shortest queue. So workers that are processing faster get more work, workers that are slower get less work. And then the system basically just adapts itself to how things are currently running. So another trick that Presto can do to be fast is operating on compressed data. Dictionaries are a common way of encoding data. So if you have strings, you typically pull out the strings, pull out the unique list of strings, and store them separately as a dictionary, and then the rows reference into the dictionary. And then if you're doing something expensive on those, like for example, you're running a regular expression, which are very CPU intensive, you run the regular expression once over all the unique dictionary values instead of doing them repeatedly over the decompressed data. And so you might have a table that has 1 million rows, and then you only have 1,000 unique strings in the dictionary, so now you've made your query 1,000 times faster because you've done 1/1000th of the work. It turns out that sometimes processing the dictionary isn't the best way to do it, because you can end up with highly selective queries, and then the dictionary actually ends up being larger than the actual output rows of the filter. So Presto has some heuristics to figure out, is dictionary execution working? And it basically keeps track of how many rows am I processing versus like how many things in the dictionary am I processing, and then it can turn off that optimization on the fly based on the actual data and query that's running. We can also use dictionaries to speed up building hash tables. Joins can produce dictionary encoded data that helps downstream processing. So you might have a join, and then you have as a subquery, and then you have another query on top of it, or that can take advantage of that dictionary encoded data. So here's an example of how we lay out data in memory. We have 2 different pages of data with 3 columns. Within each page, the data is columnar. We can see that, like for part key, those are just numbers directly. For shipping instruction on the right, we have a shared dictionary in purple that's shared between both of the pages, and then the value for inside the page is indexes into the dictionary. So we can see here that there's about 15 values in the table, and there's 4 values in the dictionary. So here, if you need to process that column, it's cheaper to do it on the dictionary first. It's cheaper to do it on the dictionary than to do it than it would be if you decompressed all the data first. So writer scaling is another thing we had to add to Presto for the batch ETL use case. Batch ETL is all about writing data, and you have queries that write a whole lot of data, and their performance is dominated by how many writers you can have. So the previous way we did it is we would just pick a fixed number of writers up front. So we'd say every query you're going to have 200 writers. And that works okay, but you've got the problem that for queries that write a huge amount of data, it's not enough. And then not all queries write a lot of data. Some queries actually end up writing very little because they're doing aggregations, or they're just not a big query. And then you end up creating way too many small files. And having a lot of small files is bad because they're expensive to read later, because you've got all the overhead of opening them and scheduling them and getting the metadata for them. And they're also very inefficient for the storage system. Our storage systems are typically bottlenecked on disk IOPS. So, reading a megabyte of data in a single read is much better than reading a megabyte of data with 200 reads. So what we do is we make Presto adaptive, and we add the writers as we go. So we start off with 1 writer. We keep track of how much data is being written. We keep track of the people producing data. When the things producing data for the writer are blocked, basically they have output buffers. When those buffers become blocked, that means that we need more writers, because writers are the bottleneck, so we add more. And there's a configurable threshold that lets you tune, that lets you make a trade-off between file size and query performance. And that lets us have lets us enforce a minimum average file size. So like think in our clusters, we tune that to 32 megabytes because we want fairly decent sized files. We rolled this out into production, and our average file size increased by 10x, which was a huge win for our storage systems. So another thing Presto does is it generates code for every single query and for different parts of the query. We basically take the SQL, we turn into JVM or Java bytecode, and then the JVM JIT turns that into optimized machine code. Examples of this are we generate code for filters, we generate codes for projections based on the actual data types of all the columns. You can generate sort comparators, or we code generate pretty much everything for aggregations. Having actual generated code lets the JVM JIT do a lot of nice tricks, like it can auto-vectorize stuff. It improves CPU branch prediction or register use because it's not having to interpret generic code. Instead of having to run a generic loop where you're doing virtualized calls over different data types, we can generate calls that are for the exact type at that point in the expression. And that allows the JVM to do inlining of that call, which can have drastic performance increases. And one of the cool things about the JVM is that it does profiling. So that's how it figures out when does it need to generate machine code and how should it generate the machine code. And it's got a number of different strategies for generating code based on how stuff is actually running at execution time. So if you have a generic loop that's used for every single query, that profile is not going to be very useful because it's polluted with the profiling information from all the different queries. But by generating custom code for each query, the profile is specific to that query and that task. And even more interesting is that that profile can actually change as the query executes. So you might be running over time series data, and the data for yesterday is quite different than the data for today, and the JVM JIT can actually recognize that and change the generated code at runtime while the query executes. So here's an example of an experiment that we did to see how effective bytecode generation actually is. This is for an aggregation where we do a number of transformations on the data before it goes into the aggregation. So we can see the naive one that doesn't do code generation, it basically scales linearly with the number of transformation expressions that you add. Whereas the generated code scales quite nicely as the expression gets more complicated. And this matches up what we actually see in practice is that basically simple queries, they benefit some, but it's the really complex queries that are where code generation really helps out. Basically, like the more complicated the query, the more benefit you get from code generation. And finally, fault tolerance is a question that comes up a lot. If a Presto node crashes, all the queries that are running on that are going to crash. And so we often get people asking, hey, does this mean like I shouldn't run my ETL on Presto because it's not reliable? The answer is no. Actually, we use Presto for ETL very heavily at Facebook, and it works out quite well. In practice, we actually don't see that many crashes due to node failures. Like modern machines are quite reliable. I think in the last week, we haven't seen a single node crash in any of our production clusters that have caused failures. And it's actually a trade-off. So you can have systems like MapReduce that write everything to disk all the time, and that's quite expensive for a number of reasons, whereas Presto can be 5 to 10 times faster because it doesn't do checkpointing. So we found it's actually cheaper to simply rerun queries on failure, on the rare cases that things fail, than make everything slow by having to do checkpointing. At the same time, we try to stay on the correct side of this trade-off by limiting query runtime to a few hours, because if you're running query for 2 hours and it crashes, then you wasted 2 hours of work and you have to spend another 2 hours to rerun it. But at the same time, we've seen jobs that take 12 hours in MapReduce and then run in a few minutes in Presto. So it's hard to say that my query that's running all day in Hive is going to run all day in Presto as well. Often the longest running queries in Hive are the ones that have the biggest speed up in Presto. And today we have clients retry on failure, and in the future we're going to put that directly into Presto. So that's it. Any questions? Yes. So the question is, are all the optimizations in the open source version of Presto? And the answer is yes. Everything we do in Presto is open source, with the exception of like a few connectors to internal Facebook systems. But we do all of our development in GitHub. You can see all of our development in the open, and we run the open source version of Presto at Facebook. Yeah, so the question is, do we use Raptor for the underlying store for most of our compute? The answer is no. So the majority of our compute is for the warehouse at Facebook, which is a system that's based on Hive. Like we use Hive formatted tables, and we have a distributed storage system like HDFS. We use Raptor most heavily for A/B testing. Raptor is a columnar storage engine that's native. That's basically turns Presto into a standalone columnar database similar to like Vertica, and it lets you lay out the data in specific ways. Like we can do collocated joins, or we can do other optimizations, which is the only reason that things like the A/B testing use case would work.
What kind of benchmarking tools that you guys use to basically when you iterate on the Presto source code, how do you measure its performance, pre and post? I saw a lot of charts. I was wondering if you had like a standard way of measuring them.
It's a great question. Now the question is like, what kind of benchmarking tools do we use to optimize the code? So it's actually an area that we need to invest in more heavily. We have a benchmark runner in the open source distribution of Presto, and we use that internally at Facebook. We have a system so we have a couple things that we do at Facebook to benchmark and verify. So every night we use the verifier, which is also part of open source Presto, that it'll download a subset of queries from production and then run them against production and against the candidate release and verify that the results are correct. So that's how we do correctness testing to make sure that we're not introducing regressions. And we actually find like quite a number of things that without the system that we would have been shipping correctness bugs. And we have a similar system for benchmarks, although we need to do a lot more work in that area. Another thing we do is that we do a lot of isolated testing using JMH. JMH is a standard profiling tool for Java that lets you basically write custom benchmarks to say, like, how fast is this aggregation function, or how fast is this join function? And then anytime we're doing performance work on a low-level component, we're like, all right, can we make joins 10% faster? We'll use JMH to test that part in isolation.
Okay. I have another question, actually. So you mentioned like it's a very, the splits are computed kind of on the fly because it makes sense. But one of the challenges there could be, how do you predict the cost of the query before it executes? Sometimes you get a mix of workloads. So would that make it harder for us to separate loads based on the cost of the query? Like, is there a predictive part into the Presto?
Yeah, great question. So that's, if we're enumerating work as we go, how do we know how long a query is going to take? So in general, knowing how long a query is going to take is like an open area of database research. I think it's kind of like a fundamentally unsolvable problem, and there's lots of like research on how to like better estimate. So because like we don't enumerate work up front, you can't even know, for example, what percentage of the input have I read, which can definitely be a problem. But then you also might you might have a join, or you might have aggregations where you're actually the data is expanding. And so, like in general, it's impossible to know, even given a fixed set of input data, if you don't know how you're going to process it, you don't know like how long it could potentially take, because like a join could increase the data set by 10x. So it's a hard problem. One thing we do in our batch systems is that we run the same queries every day, I mean, like the data changes from day to day, obviously, but like in general, the queries are pretty predictable. And so the ones that are predictable, we can actually classify them. We can say, okay, this query yesterday took an hour and it used this amount of memory, so when we're going to schedule it, like let's assume it's going to be similar to yesterday. But for inactive use cases, you really just have no idea, because effectively, a query is an arbitrary program over an arbitrary set of data, and there's not a lot you can know.
This is more a Qbol and a Presto question. In some of the Hive clusters, in Qbol, we try to use spot instances. So for stability, or like what I'm seeing, should we be even using spot on ad hoc Presto clusters? Because spot nodes do get taken away randomly, or?
So I'm not familiar with Qbol's offerings at all, actually.
Okay.
But like in general, I would say use whatever works for you and like is most cost effective.
But the node loss would make it unstable, right? If the node loss is happening constantly.
Yeah, so Presto will not run well if your nodes are, if you have bad hardware, if your nodes are unstable. We actually had that problem at Facebook where we had hardware clusters that were basically end of life, and for whatever reason, like we had to run them like beyond the expected lifetime of the machines, and they would crash all the time, and it's really bad. Basically, like the system assumes that you have fairly stable hardware.
So I was about to ask about the cost-based optimizer that you guys implemented recently, if I'm not confusing. Basically, the question was like, how did you deal with the problem without cost-based optimizer? But you already answered the question. So my next question would be about the workload management. Considering you have this hundreds of users working with the same cluster, you want to make sure that you schedule resources between them appropriately, like having some priority groups and making sure that some user doesn't consume all the resources, making like everybody stay waiting for him. So how do you right now deal with that problem? Because from what I have seen so far, Presto doesn't have any like comprehensive commercial, great workload manager.
Yeah, great question. How do we deal with resource management? That's actually something that we're working constantly on. As you mentioned, like commercial systems often have better resource management, and that's something that they've built up over many years based on customer demands, and we have the same kind of demands internally. So Presto has a system called resource groups, where you can basically build a tree of groups that each have different resources, such as soft memory limits or number of concurrent queries, and you can categorize. You can configure it so that queries go into different resources based on different properties, and that's actually pluggable. The built-in one loads a JSON configuration file. And there's also one, I think, built-in that can read from a database, or you can write a plugin that has your own. And we're constantly working on more system for the resource group management.
So in the ETL side, I see that you have mentioned of a workflow management thing, right? So is it a part of open source Presto distribution, or it is an in-house, the Facebook's in-house thing?
No, unfortunately, it's a completely separate system that's very internal to Facebook, like it's tied into all sorts of things.
Okay.
But like my understanding is that Airflow was built by Airbnb people that came from Facebook based on like what they liked about Facebook's system. So that would be my first project to look at.
There is a known bottleneck that we have come across with the master node, especially. Can you talk a little bit, and there have been some chatter in the open source regarding how to make the master HAs. Is there known patterns or stuff to make it more highly available? Because that seems like a single point of failure, apart from the workers crashing themselves.
Yeah, so the question, how do we deal with there only being one coordinator and the coordinator becoming a bottleneck? So one thing we do is we limit the size of our clusters. I think our biggest cluster is around 800 nodes, and then we'll just stamp out a whole lot of clusters of that size. And the CPU usage of the coordinator actually can be a bigger deal for things like the app analytics use case, where we've got hundreds of queries running at the same time, and they're just cranking through queries because they're all really short. That actually uses more CPU on the coordinator. But we recognize that we have the problem that having a lot of clusters and having a lot of and only having one coordinator is a problem. So we're working on a system to pull parts of the coordinator out separately. We're working on a dispatcher now, which will basically move all the resource management into a separate kind of master coordinator that will then dispatch work to the individual coordinators. And then I think we're going to move to a direction where we actually we pull out the coordination work for individual queries, so you can actually have multiple coordinators in the same cluster and then eliminate that bottleneck. So I'd say for today, have multiple clusters, and hopefully by the time you reach these limits, we'll already have hit them and have solved these problems.
Thanks, good to know.
Great, thank you, David. Let's show David a big round of applause. Thank you very much.